Alright, welcome to lesson 10.04. Here we're going to continue applying the method of substitution, and we're going to use it now to evaluate definite integrals. Let's go ahead and get started. Alright, so this seems like a rather long discovery problem, but you don't need to copy down any of this whatsoever. You just need to write down the integral that we are trying to evaluate and follow the instructions here. So our goal is to evaluate the definite integral from 0 to 2 of the square root of 2x plus 1 dx. Now remember that we can interpret the value of a definite integral with respect to the area under the curve of the function we're integrating on that interval. So to get an idea of what this definite integral will have a value of, let's sketch a quick graph and illustrate the area that corresponds to the value of the definite integral. So I have two graphs here. Do that on one of the graphs and then create an identical looking x and y axis, one for x and one will be for u. Alright, do part A and we'll take a look together. Alright, so here's my curve, and I am looking at the definite integral from 0 to 2, so I can interpret the value of that definite integral as the area under this curve between 0 and 2. So I've gone ahead and shaded that in, and to get sort of an estimate of what this value might be, consider that the square root of 5 is going to be a little greater than 2, and so you might say, okay, well this purple area is probably a little less than a 2 by 2 square, which would be an area of 2. Alright, so now that we have this quick sketch, we want to make the u substitution for our integral here. And when we do that, we can rewrite our integrand in terms of u so that it is easier for us to anti-differentiate. So make the u substitution and rewrite your integral, but don't choose your limits of integration yet. So I want to make u 2x plus 1. Remember, if I have a composite function, we always want to try using the innermost part. And I know this is going to work because the derivative of this is just going to be 2, and so I can handle a constant, and I'm going to be able to rewrite du in terms of dx nicely. So I'll go ahead and do that now. And once I have du dx, I can solve for du, and doing so gives me 2 dx. And now looking at my substitution, the inside of my radical is going to be u, and then I'm going to have an expression for 2 dx. But notice I don't have 2 dx, I simply have dx. So I want to rewrite this expression so that it's solved for just the piece I need left, which is dx. And that requires me to multiply by 1/2 on both sides. And so doing so gives me 1/2 du equals dx. And now I can make my substitution. Alright, so doing so allows me to transform my integral into 1/2 times the definite integral. Notice I've left the limits blank. I'll leave some blank spaces there. Of the square root of u du. Now we can interpret this definite integral in the same way that we did this definite integral, as the area under a curve. It just seems now that our curve is a little different. So let's go ahead and take a look at our curve, square root of u, by graphing it here on the axis, where now our x-axis is actually representing the variable u. So we can graph the square root of u pretty easily. It'll look like this. Now, let's take a look at the function in terms of u, and let's ask ourselves, what should our limits of integration be? What I want you to do is think if it makes sense to keep the original limits of integration, in other words, from 0 to 2. So analyze the area under the curve, remember that we're multiplying by 1/2, and decide whether that makes sense. So just by looking at the area under the curve square root of u between 0 and 2, I see that this area already appears to be less than the area that represents our original definite integral. And so when we multiply by 1/2, certainly we're not going to end up with the right amount of area. And this makes sense. There's no reason to think that we should keep the same limits of integration. After all, this definite integral was with respect to a totally different integrand than we have here. So the question becomes, how do I figure out what these limits should be? Well, it's a pretty simple step. All we're doing is taking an x value and finding out what its corresponding u value would be. So we have an equation that gives that to us. Given an x value, I can find a corresponding u value. So what I want you to do is try this on your own. Find the corresponding u value when x is 0 and when x is 2, and use those as your limits. Once you've decided on those limits, press play, and we'll take a look together. Alright, so notice what I'm doing is I'm trying to figure out the corresponding u value when x is 0 and when x is 2. We're going to use our u substitution because that is the way that we transformed from a variable in x to a variable in u. So u of 0, the corresponding u value to when x is 0, is going to be 2 times 0 plus 1, which is 1. The corresponding u value for when x is 2 is going to be u of 2, which is 2 times 2 plus 1, or 5. So that means that my new limits are going to be from 1 to 5. So notice that all I had to do was find the corresponding u value for my lower limit, u of 0, that became my new lower limit, and find the corresponding u value for my upper limit, and that became my upper limit. Now that I have this definite integral here, notice that we can fully evaluate this. There's no need to go back to a variable of x. We can evaluate this perfectly fine without doing so. So go ahead and evaluate this definite integral here, keeping it in terms of u. Go all the way through till you get to the very end, and then press play, and we'll take a look at the final answer together. Alright, so here is the solution. I'm going to evaluate this definite integral using the fundamental theorem of calculus. So the antiderivative of u to the 1/2 is 2/3 u to the 3/2. I'm going to evaluate at 5 and at 1. Subtract. I can factor out the 2/3 because that's a constant. So I have 1/2 times 2/3. That gives me 1/3. And then I have u to the 3/2 evaluated at 5, which is just going to be 5 to 3/2. And u to the 3/2 evaluated at 1 is just going to be 1 to 3/2, which is 1. Now notice here that 5 to 3/2 is perfectly fine, but I can rewrite this, and I can take advantage of the fact that 3/2 is 1 plus 1/2. And when you're adding exponents, that means you are multiplying a base of 5 to the 1 times a base of 5 to the 1/2. When you multiply the same base, you add the exponent. So 5 to the 1 is 5, and 5 to the 1/2 is square root of 5. So I can rewrite this as 1/3 times 5 square root of 5 minus 1. So looking back at our work, we want to pull out some key points here. Notice that when we are evaluating a definite integral using u substitution, we have to make sure that we transform our limits from values of x to values of u using the substitution that we made. And once we do so, we'd never have to go back into a function in terms of x. We can actually evaluate this definite integral, keeping it in terms of u, and that actually makes a kind of a little less work on the back end of the problem. Alright, so I want us to add to our notes on u substitution. These are the notes that we took already for indefinite integration, meaning when we're just finding the antiderivative without any limits, and we can use a u substitution to do that, and we need to make sure that we resubstitute back into our original variable, because what we're trying to do in that case is actually find a solution to a differential equation, and we want it in terms of the variable we started with. When we are evaluating a definite integral, we don't care what it looks like along the way. We just want to find the value for that particular definite integral. And so what we want to do is analyze the integrand, and if we need to make a u substitution, we choose our u appropriately. We take the derivative of u with respect to x, solve for du, and then we rewrite our integral in terms of u. In doing so, we need to make sure to convert the limits from x to u. And so I've drawn this diagram here to explain that. If we are going originally from a to b for our integral in terms of x, when we rewrite our integral in terms of u, we want the lower limit now to be u, the u that we chose for our substitution, u evaluated at that x value a, the lower limit, and the upper limit to be u evaluated at b, whatever the upper limit was. That's how we're going to transform our limits. And then at that point, we are ready to actually evaluate our definite integral. So notice that this is actually, because of this little built-in step here, a little bit easier in some ways. But regardless, the key point to take away is that whether we're evaluating an indefinite or a definite integral, if we have a situation where we can't integrate sort of straight out just by looking at it and finding the antiderivative, making a u substitution can really help that process become a lot easier. All right, let's take a look at an example before you get on to the homework. All right, so here is a definite integral for you to evaluate. Go ahead and follow the process. Try this first on your own. At least make a u substitution and try and transform your limits as well. And then even if it doesn't work out, that's okay. It'll actually be beneficial. Then press play and we'll take a look together. All right, so in evaluating this integrand here, I noticed that the innermost part of my composite function is this x squared plus 16, and I'm drawn to that because I also see an x. So I know the derivative of x squared is 2x, and so I can handle that constant too. The important piece is that I'll have an x there. So I'm going to let u be x squared plus 16. Then I want to solve for the differential of u, and doing so will give me du is equal to 2x dx, as I have shown right here. Now notice this is very close to what I want. I have x dx, and this is 2x dx, so to account for that, I'm going to multiply by 1/2 on both sides, and now I'll be able to substitute in everything by inputting a u here and a 1/2 du for the x dx. But before I do that, I need to make sure that I also know what my limits of integration are going to be. So I need to compute u of 0 and u of 3 for my lower and my upper limit. Not too bad to do that. U of 0 is 0 squared plus 16, or 16, and u of 3 is going to be 3 squared, or 9 plus 16, which is 25. So my new limits of integration are going to be 16 and 25. And now I can rewrite my definite integral with my full u substitution. And I have done that here. Notice a couple of things I did. At first I just input all the pieces, square root of u, and then x dx, which is simply 1/2 du. And then I factored out the 1/2, and I brought the square root, which is u to the 1/2, into the numerator to make it u to the negative 1/2. And now I can take the antiderivative and evaluate it 25 and 16 and multiply by 1/2. In other words, use the fundamental theorem of calculus to evaluate. And this ends up being really nice and easy. The antiderivative of u to the negative 1/2 is going to be 2u to the positive 1/2. Factor out the 2 here. 2 times 1/2 is 1. U to the 1/2, or just the square root of u. Evaluate at 25, square root of 25, minus, when I evaluate this at 16, square root of 16, 5 minus 4 times 1 is 1. So the value of this definite integral is 1. All right, before you go into the homework, there are a couple of good examples to take a look at. If you go to page 345 in your book and look at example 8 and 9, both of those are definite integration with u substitution, and are a couple of sort of different scenarios that you could see, and it's good to get as much exposure to u substitutions as you can. So even if you don't do the whole problem, taking a look at those and just seeing the u substitution that was made will be really helpful and pay dividends as you work on the problems.